everyone, so we are in chapter 2 atomic structure, 2.1 Bohr's atomic model. Part 1, you will learn about the Bohr's atomic postulate and line spectrum of hydrogen atom. In this part, you will learn about the Bohr atomic postulate and line spectrum of hydrogen atom. In Bohr's atomic postulate, there are 4 postulates. First, electron move in circular orbit around the nucleus. Let's say we have proton with the positive charge in the nucleus and electron with the negative charge. Energy level, it also known as a stationary state or orbit. And in this diagram, I show you until n equal to 3. N equal to 1 is the lowest energy level, and in this diagram, the highest energy level is 3. When electron moving around the nucleus in the circular orbit, it does not release or absorb any energy at stationary state. Second, in the specific energy level, we refer to the n equal to 1 or n equal to 2 or n equal to 3 and so on. The energy of electron is fixed in value or is quantized. What is meant by the quantized? Quantized means fixed or a definite amount of the energy or specific amount of the energy when electron at its stationary state or at its energy level. When an electron moving in an orbit, it can have a certain amount of energy. So, how can we calculate the energy of an electron? By using this formula, En equal to negative RH. RH is the Rydberg constant, and this is the value for the Rydberg constant, 2.18 times 10 to the power negative 18 joule, in bracket 1 over n square. N is the principal quantum number or energy level, integer 1, 2, 3 and so on until infinity. For the example, if the electron at n equal to 1, so E1 equal to RH 1 in bracket 1 over 1 square. Okay, because the n equal to 1. Okay, this is the calculations for the energy electron at n equal to 1. For the electron at n equal to 2, you must write E2 equal to negative RH in bracket 1 over 2 square. Okay, so this is the calculation for the electron at n equal to 2. So the energy of the electron when it at n equal to 2 is different when the electron at n equal to 1. Third, an electron move in an allowed energy state will not absorb or radiate energy. There is no change of energy while electron move within an orbit. And the last one, energy is emitted or absorbed by an electron as it changes from one allowed energy state to another. For the example, initially electron is located at n equal to 1. So, when it makes transition from the lower energy level n equal to 1 to higher energy level n equal to 3, it will absorb energy. So the electron, it will absorb energy when it makes a transition from the lower energy level to the higher energy level. And the electrons, when it makes transition from the higher energy level to the lower energy level, it will release energy. Okay, so for the fourth postulate, it states that the transitions of an electron from the different energy level, it will absorb energy or release energy. So emitted means release. So these are 4 postulates that you need to know. Okay, this is an example when an electron makes a transition from the lower energy level n equal to 1 to n equal to 2, so energy is absorbed. Okay, when an electron makes a transition from the higher energy level n equal to 2, okay, or in other words, it falls back to the lower energy level n equal to 1 from it makes transition from the n equal to 2 to n equal to 1, so energy is released. Okay, type of spectrum. There are 2 types of the spectrum: continuous spectrum and line spectrum. So this is the example of the continuous spectrum. You can see that it's just like rainbow, but for the line spectrum you can see it clearly line. Okay, the spectrum in the line form. Okay, this is a line spectrum. So this is a hydrogen emission spectrum, and this is how to get the continuous spectrum and line spectrum, okay, by using the prism. And what is the difference between the continuous spectrum and line spectrum? For the continuous spectrum, you can see that it is a spectrum that consists of all wavelengths in the visible region. Okay, you cannot determine the specific wavelength for the continuous spectrum. So you can determine the wavelength by its range. And there is no blank area. You can see that there is no blank area for the continuous spectrum. And the source is the white light, sun, moon, and etc. Okay, line spectrum. We refer to the spectrum of the radiation that consists of discrete line with the specific wavelength. Just I told you, you can see that for the line spectrum, you can see clearly it is a line. So each line, it has specific wavelength. Okay, and each line is separated by blank area. So actually this is a blank area. Okay, between the line there is a blank area, and the sources is the light of the discharge tube of the hydrogen, sodium, etc. Okay, this is a 2 type of the spectrum. Okay, now let's see how the line spectrum of hydrogen atom is produced. Alright, for the example, okay, I still using this diagram. Okay, we have the nucleus and we have the electrons. Okay, so the energy level, okay, I give until n equal to 4. So when, let's see the first point. Okay, when the question asks you to explain how the line spectrum of the hydrogen atom is produced, so you have to start with this point. When the electron of a hydrogen atom at its ground state lower energy level absorbs sufficient amount of the energy, it will move to the higher energy level. So let's say if the electron is located at n equal to 1. So when it move to the higher energy level, for the example, it move to the n equal to 2, it will absorb sufficient energy. So it will when it absorbs sufficient energy, it will excite to the higher energy level at n equal to 2. So what happened at higher energy level, we refer to the n equal to 2, okay, where the energy level, the electron is excited. The electron is unstable. So when the electron excited to the n equal to 2, okay, higher energy level, what happened is the electron is unstable. So it will fall back to the lower energy level. So from this diagram, I show you the electron makes a transition from the n equal to 2 to n equal to 1. And this is the energy profile diagram. Okay, energy profile diagram, y-axis for the energy, and here, okay, I give you a line. Okay, this is a energy level or stationary state. So here I give you n equal to 1, 2, 3 until the last one is the infinity. And to draw this energy profile diagram, okay, you have to make sure that the scale is not same. Okay, you can see that when it's going up, okay, the line getting closer. All right, so this is how you draw the energy profile diagram. So by using the energy profile diagram, here I show you when the electron at n equal to 2, okay, the electron at the excited state, so it will fall back to the lower energy level n equal to 1. Okay, then what happened during the transitions? Okay, it fall from the higher to the lower energy level, and energy will be released in the form of light. Okay, when an electron makes a transition from the higher to the lower, it will emit photon. You will see it in the form of light at definite wavelength. So it will produce line spectrum here. Okay, so this line, it has a specific wavelength and certain frequency. So since energy is quantized, the line spectrum is produced. So this is how the line spectrum is produced. Okay, let's see next line. Okay, let's say if the electron when the electron absorb energy and it excites to the n equal to 3 here. So what happened when it makes transition from the n equal to 3 to n equal to 1, 3 to 1, so it will release energy in the form of photon. You will see it in light form, and the line spectrum is produced. So this line spectrum, it has specific wavelength and certain frequency. Okay, let's see another one. If the electron at n equal to 4, okay, it makes transition from the n equal to 4 to n equal to 1. Okay, from 4 to 1. So it will release energy in the form of photon. Okay, you will see it in light form. And then this line, it has a specific wavelength and certain frequency. So line spectrum is produced. Okay, so there are 3 diagrams here. I show you. This is the atomic model, and this is the energy profile diagram. Okay, and this one is the line spectrum. Okay, this is a line spectrum. So from the left to the right, okay, the energy is lower, shows that this line, it has the lowest energy. Okay, if you can see that this one, it makes lower transitions. Okay, but this one, it makes larger transitions. So larger transitions, it will release more energy compared to this one. Okay, so from here to here, the energy is decreased, and the wavelength is higher. So it shows that this line, it has the lowest energy, but the wavelength is the highest. And this line, it has the highest energy or larger energy because the transition is larger. Okay, but it has the lowest wavelength. And you can actually this formula you will learn in the second part, but I show you what is the relationship between the energy and wavelength and also the frequency. So when the electron makes a transitions, okay, there will be energy change. So this is the energy change equal to the h nu. Nu is the frequency. So if the difference energy is larger, the frequency will be larger. So nu, the frequency also equivalent to the C over lambda. Okay, I will explain to you about this formula in the second part, but I just explain, okay, what is the relationship between the delta E and wavelength. So when we change, okay, frequency to C over lambda, okay, so you can see that if the difference energy is higher, the wavelength will be lower. So for this line, it has the larger difference energy, but the wavelength is lower. And this line, it has a lower energy, but higher wavelength. Okay. And one more thing, you can see that the distance, okay, between this line and this line is more closer compared this line and this line. So the farthest line, this one, okay, is the first line. First line means that transitions of the electron from the 2 to 1. Okay, this is the first line, and this will be second line, and this one is the third line. Okay, emission series of the hydrogen atom. As you know that in 1 mole of the hydrogen atom, there are Avogadro number atoms of the hydrogen. So the electron in each of the atom is not same. Okay, maybe the electron for one atom is at n equal to 2, and another atom, the electron is located at n equal to 4. Okay, because there are Avogadro number atoms in 1 mole of the hydrogen atoms. So, okay, there are 5 possibility spectrum, okay, can be produced, which is we have the Lyman series, okay, we have the Balmer series, Bastian series, Brackett series, and P-Fan series. So this is the various series in the atomic hydrogen emissions. So when electron makes transitions, okay, from the higher to the lower, okay, it will form maybe it can form Lyman series, Balmer series, Bastian series, Brackett series, or P-Fan series. If the electron drop to the makes transitions and fall to the n equal to 1, so it is Lyman series. Okay, and what is the spectrum region for the Lyman series? It is ultraviolet. Okay, this one is the Lyman series. And for the Balmer series, when an electron makes a transition from the higher energy level, okay, we refer to the 3, 4, 5, 6, and so on until infinity, and it fall back to the lower energy level, which is it fall back to the n equal to 2. So it will form Balmer series. Okay, and the Balmer series, it is in visible region. So visible region, you can see the color of the line, just like this one. So only the Balmer series has the color. Okay, compared to the others, okay, only black line. Okay, so only Balmer series has color because it is in visible region. Okay, if electron drop or fall to the n equal to 3, okay, so it is in infrared region. So this is the infrared region. So in infrared region, we have the Bastian series, Brackett series, and P-Fan series. The difference is when the electron drop to the final energy level, which is if the electron fall back to the lower energy level equal to 5. So what series is formed? It is P-Fan series. Okay, let's see the example. The following diagram represents the line spectrum of hydrogen atom for the Lyman series. Okay, it states that it is Lyman series. Shows that the electron drop to the n equal to 1. So this is the line spectrum. Okay, and we it labeled with the A, B, C, D, and E. Okay, specify the increasing order of the radiant energy, frequency, and wavelength of the emitted photon. Which of the line that correspond to fault line? Okay, the farthest line, I told you, is the first line. So this is the first line. For the Lyman series, the first lines, we refer to the transitions of an electron from the n equal to 2 to n equal to 1. So this is the first line. So from here, you can determine that B is the second line, C third line, D is the fourth line. The shortest wavelength, okay, because A is the first line, it shows that it has smallest transitions. So the difference energy is lower. Okay, A line has the lowest difference energy, shows that it has the higher wavelength. So the shortest wavelength, we refer to the largest or highest difference energy, which is E. So the shortest wavelength, we refer to the E, with the highest difference energy but shortest wavelength. Remember the formula I show you, delta E equal to the Hc over lambda. So if the difference energy is higher, the wavelength will be lower. Okay, the lowest frequency. Lowest frequency, we refer to the line with the larger difference energy. Lowest frequency, we refer to the lowest difference energy. Okay, because by using the formula delta E equal to the H nu. So the frequency will be lower if the difference energy is lower. Alright, it is directly proportional. Delta E directly proportional to the frequency. So the answer is A. Okay, that's all. Next, we see this part 2.